All right, so for the next few sections, we'll be focusing on volumes. So we're going to be looking at 3D shapes. So we're going to have to actually be able to graph in 3D just to make sure that we know what we're looking at before we actually start doing it. To start with, we're going to first take what we know in 2 dimensions and just sort of scale it up. So we'll start out just by remembering what happens in 2 dimensions when we want to find an area. So we have some function and we want to find the area underneath it. So it'll typically look something like this. This is the area we're looking for, right? And so what we'll do is we'll kind of walk through the Riemann sum kind of thing that we did. We notice that rectangles kind of fit nicely in here, or trapezoids, or whatever we want to do. And we would typically find the area of one of these guys, right? We're going to use f of x to find this height. And we'll call this guy here delta x, right? The thickness. And what we do is we make all these rectangles next to each other that fill in the whole space. And then we find all of the areas of those rectangles, add them together, and that gives us the area of the whole region. And then to go from Riemann sums to integrals, we take this delta x, have it approach 0, so that these are infinitely thin rectangles. So the idea for taking that into volume, we'll keep our horizontal axis horizontal, but we'll take our vertical axis and kind of put it off at an angle close to 45 degrees there. And what we'll do then is we'll say have some sort of shape that's sticking out of our axes. And it's going to have some sort of boundary on it. And what we're going to need to have is we're going to need to have, oops, let's see, this should have a pretty solid stopping point there. So let's make some shape and then make it maybe go like this. And so what we're going to need to do is if we have some shape, we're going to need to know what the cross sections look like. So imagine kind of we've got these different cross sections here sticking out, and we've got an infinite number of these guys, and so we can kind of see a 3D shape kind of maybe sticking off the page. So what we're going to do is we're going to take a look at one of these cross sections, say this guy here, and try to draw along the base here. Close enough. And what we're going to do is we're going to say pretend that we have a 3-dimensional chunk here sticking on top of our base. All right, that's going to have some sort of area here, the area of this cross section, and that's going to be dependent on x. So different places that we make these cross sections will have different areas. And so we'll also have some sort of thickness. We will call this delta x, or oops, just get ahead of myself there, delta x. And so we'll make a bunch of these cross sections, find their volumes, and then add them together. The volume of one of these cross sections is going to be a of x times delta x. Right? Because the area is already going to be 2 dimensions, we're adding this 3rd dimension. And so what will happen is we'll end up making the thickness of these cross-sectional pieces infinitely small. And so we'll just have a of x times dx. Right? And that's how we go from kind of the Riemann version into the integral version. So we're going to start from a, go all the way to b. That's where our base is going to start and stop. Right? And the cross section has to be known. It's got to be an integrable function, and typically it's going to have to be something that we can actually deal with, as in we can find the area of it. So something like maybe a rectangle, a square, a semicircle, something like that. Something that we know the area of. And so we can integrate the area from a to b, and that does this process. All right, so a of x, cross-sectional area, dx is the thickness. Right, so we'll go ahead and take a look at this image here. I don't want to use too many of these or rely too heavily on these because we need to be able to draw these situations reliably. Because oftentimes we're not going to have pictures. We're going to have to kind of make it ourselves if we want to visualize the problem. So I don't want to rely on these too much. But just as an aid here, we can see that for this one, all right, if I pull X all the way back, this is a solid shape sticking out of the plane here. And that's going to be our red-orange guy. And this this blue plane here, you can see that it's sort of tracking our cross sections, and it looks like all the cross sections here are parabolas. But we notice that as X goes to different spots along this base, the cross sections are either bigger or smaller. They're going to have different areas, which is why we're going to have A of X. We're going to have some sort of tracker to make sure that we're being aware of how our X influences the area. All right, so we'll go ahead and take a look at one here. And we're going to try drawing it, and then we're going to sort of look at that just as a vindication for us here. All right, so when we are given a solid with a base bounded by curves, we're going to need two different graphs. Firstly, we're just going to need to graph the base itself. All right, so we'll just graph these two. So we got y equals x squared. That's a standard parabola. And so that's going to be vertex at the origin. If we go left and right 1, we go up 1. If we go left and right 2, we go up 4 from that vertex. So something that looks kind of like this. Kind of. The other guy here is going to be y equals 2 minus x squared. That's minus x squared plus 2, which is a downward opening parabola whose vertex is pulled up 2. So left and right 1, down 1. So we're actually going to be going through the same points there. Coincidentally, that's the intersection, which is important. If we go left and right 2, we go down 4 from the vertex. All right, so we're looking at something kind of like that. And so we're looking at the base is bounded by these curves. So it's going to be the space in between the curves, or this guy right in here. Cross sections through the solid perpendicular to the x-axis are semicircular disks. So our cross sections are going to be vertical like this. Like this. There you go. So we're looking at it straight on. So really we should be having kind of semicircles sticking out of the page. It's really difficult to show that though if we're looking down at our solid. So what we want to do also for these kinds of problems is draw a perspective view. So try to get that horizontal x-axis and then the y-axis that's maybe 45 degrees off here. And we're going to make the solid base again. So we're going to need some hash marks. Our hash marks should be parallel to the axis next to it there, which that one's not very good. Let's try that again. There you go. And then the hash marks on the y-axis should be horizontal still. So we're looking at this point here, and these 2 points here. So we're drawing a parabola out that way. Try to get this perspective a little bit, flatten it. There you go. And another parabola pointed down like that. And so we're making these perpendicular to the x-axis slices, and on each of those is a semicircle. So we'll just make a couple of those. And you can see that as x is closer to these points, the semicircles will get smaller. On this middle, this semicircle will be its largest. Right. I'll go ahead and expand this. That's not the right button to do that though. I'll go ahead and expand this just so that we can kind of observe this a little better. Because we need the area of one of these semicircles. Let's go ahead and grab, say, the big one. The area of a semicircle is going to be 1/2 pi r squared. Right, area of a circle with a half on it. All right, so we need to determine, this is in terms of r, we need it in terms of x. So we need to figure out, how do we represent this radius in terms of x? Well, at this particular point right in the middle, it looks like we can do that just by well, if we get the diameter first, the diameter is just going to be half of that height, right? So it's going to be half of, well, this upper function's going to be represented by 2 minus x squared. But we need it in general. Anywhere that this x is, anywhere that we kind of slide the x along any of those spots needs to be represented in our area function. So we have to remember, how do we find the distance between these two functions? Last section, we looked at the area between curves. We found that the distance between the two functions is the top function minus the bottom function. So we're looking at top function is 2 minus x squared minus the bottom function. But this isn't the radius, this is the diameter, right? The distance from the top to the bottom, this guy here, is the diameter. So we're actually going to have to put another 1/2 on that. Now it's the radius. So we're looking at 1/2 times 1/2, we'll make that 1/4 pi 2 minus 2x squared squared. And let's go ahead and clean this up a little bit. We can factor a 2 out. So we'll need a bracket there. 2, 1 minus x squared squared. We can apply the square, remember, to both of the factors here. So 1/4 pi times 4, 1 minus x squared squared. And so we get pi times 1 minus x squared squared. And so our integral, if we're looking for the volume, is going to be integral from, and we have to look at what x values does our base start and stop at. Here it's going to be the intersection, right? -1 to 1. And on the inside, we are integrating our area. So pi 1 minus x squared squared dx. I'll go ahead and pull the pi out. And we're looking at our integrand here, trying to figure out how to integrate this. We're going to have to multiply this out likely. Right, we can't do u substitution because we would let u be probably the inside here. We'd have to have the derivative somewhere, -2x. And we can kind of let it slide when we've got constant multiples going on, but we'd still need an x somewhere, and we don't have it. So we'll go ahead and FOIL this guy out. 1 squared is 1. -x squared, square it, you get plus x to the 4th. And in the middle, it should be 1 times -x squared times 2. All right, so we're looking for pi times, and we'll go ahead and just run the power rule through all these. X minus increase the power of x by 1 and divide by that new power. Increase the power of x by 1, divide by the new power. And we're evaluating this guy from -1 to 1. So we've got pi times, and I'll go ahead and open up some brackets because in the first parentheses I'll plug in 1. 1 minus 2/3 plus 1/5 minus, plug in -1. -1, -1 cubed retains the negative. -1 in the 5th power also retains the negative. So we've got pi times, well, we're going to end up distributing this negative. We're going to get the same thing twice. So I'll go ahead and put a 2 out there because we are getting the same thing twice. So 2 pi, we've got 1 minus 2/3, that's 1/3 plus 1/5. That's 2 pi times 5/15 plus 3/15. That's 2 pi times 8/15, which ends me up with 16 pi over 15. And this is a volume, so it should be cubic units. Again, I'm not really going to be picky about you putting units on there, unless it's a word problem or something where we have a particular type of unit. All right. So that's the general slicing method. And so what we're going to have next then is we're going to look at the solids of revolution. So again, I'm going to try to keep things drawn as much as possible, and we'll kind of look at these as we go. So we'll go ahead and kind of work through this definition here. Suppose f is a continuous function with f of x greater than or equal to 0. Get that out of the way. Just mean that we want a function that is positive. So I'll go ahead and kind of do my generic function here. And it's going from a to b. All right, so let R be the region bounded by the graph of f, the x-axis, and the lines x equals a and x equals b. So I'll go ahead and kind of make a hard stop here at a and b. And so this guy in here is our R. This region all up in here. So what we're going to do is, it says now revolve R around the x-axis. As R revolves once, it sweeps out a three-dimensional solid of revolution. And this is going to be what we'll deal with probably most in this section here. So how do we draw then a solid of revolution? Let's go ahead and take a look at both of these images here just to kind of visualize what's going on. All right, so we're taking our region here, and we're taking that area and just moving it all around the x-axis that eventually it meets with itself. And so if we see as that area moves, it starts to produce a solid. And so we'll get some sort of solid maybe that looks like that. So this is what we want to illustrate on our picture here. And again, we're not often going to have a picture given to us, we're going to have to make it. And the best way that I found to kind of make this happen is to take the region that you've done, start with that, and then make sort of its clone down below the axis, or just on the other side of the axis you're dealing with. Then I'm going to take the leftmost point here, and I'm going to track its movement. Right, so it should move all the way down here to its mirror, and then it should move all the way around back to itself again. And I'll do the same thing over here. So this point on the right should go to its mirror, and then should go all the way back over and meet with itself again. And I'm kind of making ellipses here, just to show some perspective here, just so we recognize that it is three-dimensional. And I'll kind of pick another point, maybe another couple points in here, and do the same thing. Right, and that's probably good enough. We can see now that this is representing a three-dimensional shape. So that, in general, is how we'll go ahead and look at that. So if we notice, and we're thinking about the general slicing method, right, to find these volumes in general, we can see that all of these guys are circles, right, because every point is moving in a circle. And so if we kind of take a gander at this next image here, as we revolve, I'll take a solid off here. As we revolve, we do get a circle. And any x that we choose in a solid of revolution will give us a circular cross section, right? And that's how we get the solid that we end up with. And so we will call these disks, and we will find the volume here using the disk method. So we notice that the radius of one of these circles, which is important for finding the cross-sectional area, the radius of one of these guys is just the function height. And so if we're finding the area should be, pi r squared. And so we replace r with f of x. And that's our area. And so we are just integrating from a to b the function squared times pi. That's pi r squared. All right, that's if we were revolving about the x-axis. If we're revolving about the x-axis, we'll use dx, we'll use x's here. We can do the same thing about the y-axis. If we're doing about the y-axis, we're going to use f of y, and we're going to use dy. So at this point, it's going to be moderately easy to figure out which method we should be using. If the problem says about the x-axis, use x. If the problem says about the y-axis, use y. Later on, we'll kind of shake things up, but for now, that's what we'll do. Right, so let R be the region bounded by the curve, and we've got a standard parabola. It looks like it's been shifted left by 1, and so that's the image that we have here as well. It's already given for us. We're also bounding it by the x-axis. The lines x equals 0 and x equals 2. So we'll go ahead and draw those out. And so this in here is our region R. Find the volume of the solid of revolution obtained by revolving R about the x-axis. And so we'll go ahead and set that up. So we're going from 0 to 2. Now we'll just use the formula here. Pi x plus 1 squared. We have to square it again. I'll move the pi out. And so we have x plus 1 to the 4th dx. All right, so back on that previous one, we did have to multiply everything out because we had a squared on the inside and on the outside. Here we just have a 4th power on the outside, so u substitution can handle this nicely. So let u equal x plus 1. So du will be dx. And so we can look at integral from x equals 0 to 2 of u to the 4th du. And again, you can change the limits of integration based on u if you want. This is just how I'm going to do things. Either way would be correct. All right, so we'll go ahead and use the power rule here. Increase the power by 1, divide by the new power. And we're evaluating this guy from x equals 0 to 2. We'll go ahead and move the 1/5 out, so we get pi over 5 u to the 5th evaluated from x equals 0 to 2. So we need to replace u with x again. Pi over 5. And in here we've got then x plus 1 to the 5th from 0 to 2. And so we'll go ahead and evaluate this. Again, I use brackets so that each evaluation can have its own parentheses. We got 2 plus 1 to the 5th minus 0 plus 1 to the 5th. And so we have, let's see, it looks like 3 to the 5th minus 1 to the 5th, and I don't really need the brackets anymore. I can change them back to parentheses. 3 to the 5th. I know that 3 to the 4th is 81, so 3 to the 5th should be 243. And then 1 to the 5th is 1. So pi over 5 times 242. That's 242 pi over 5 cubic units. And again, this is all you need. All right. So we'll go ahead and move on to the next one here. Let R be the region in the first quadrant. So first quadrant means that we are definitely using a hard stop like that. Bounded by the curve 4 minus x squared. So that's a standard parabola shifted up by 4. And we can already see here that we have intersections with the axes at 0, 4 and 2, 0. Find the volume of the solid revolution obtained by revolving R, which is this guy in here, about the y-axis. That means we need everything in terms of y here. So we'll look at this as y equals 4 minus x squared, and we're going to have to solve for y. solve for x so that y is our variable. Exactly backwards. So we'll add x squared to both sides, and we'll subtract y from both sides. We'll take the square root. And so we're going to have to decide which of these am I actually using. This should be a function of both, right? It's a function of x and it's 1-to-1, so it should be a function of y as well. So which one do we do? Well, you can kind of just pick. I want to go through the point 2, 0. So 2 equals, so it's got to be positive, this one. So we're only using the positive one. So our volume will be an integral using pi times root 4 minus y squared dy. Right? That's if we're looking at how this shape should look. I'll go ahead and do the whole copying thing over here. We're going to be revolving about the y-axis, so something like that. I can't really do this end because it's got a 0 on it there, so I'll go ahead and just do a couple in the middle. So our radius is going to be the distance, right, the height of this function, but in terms of y. That's why we're using a horizontal height here. So that's our radius. We square it, multiply by pi. That's our cross-sectional area. And now we just have to figure out where do we integrate it from. This is going to be in terms of y. So we have to figure out what are the y values where the region starts and stops. So looking from the bottom up, at the bottom we start at y equals 0. At the top we hit y equals 4. And so that's going to be our limits of integration. Right. We'll take the pi out. And we'll cancel the square root with the square. So this is going to be a nice integral to handle here. So we'll go ahead and do power rule. We've got 4y minus 1/2 y squared. We're evaluating this from 0 to 4. So we've got 4 times 4 minus 1/2 times 4 squared minus 4 times 0 minus 1/2 0 squared. 4 times 0 is 0. 0 squared is 0 times 1/2 is also 0. So we're looking at pi times 16 minus 1/2 times 16. That's 16 minus 8. So we get pi times 8, which is 8 pi cubic units. All right, so that's how we do things in terms of y. It's just slightly different. So now we've kind of seen both of those. We'll see another variation on this. Variation on the disk method enables us to compute the volume of more exotic solids. So we're going to combine last section with this section. So suppose we have a region between two curves. So we have two curves here, and we take this region and we revolve that. So we're revolving this whole thing. You notice that since I'm not touching the x-axis, I end up with a hole in my solid. So if I go ahead and make this solid, I end up with a hole that runs all through it, but the hole has a different sort of thickness all the way throughout. So how do we determine the volume of this solid? Same idea, area of the cross-section. Right, notice that my cross-sections are all circles with circles taken out of them. So we're going to have a larger radius. So I'll kind of redraw it here so I can kind of label things the way I want to. So I'll make my clone here. And bulge out, come in, there you go. So we'll have kind of two radii going on here. And so just for the sake of knowing that they're different, I'm going to call the larger radius, the one that goes from the x-axis all the way to the top function, we'll call that capital R. And this is just for the sake of determining an equation that we can use here. Normally this should be a region, so we're not going to use that very much. We'll call the smaller radius that goes from the x-axis to the inner function here, we'll call that little r. So the cross section will look like this, with big R here and little r here. So how do we find the area of this shape? Well, it's going to be the outer radius here, the outer circle, sorry, pi capital R squared, minus the area of the inner circle, pi little r squared. So that's going to be how we determine this area. We can factor out the pi as well. R squared minus little r squared. Right, and now we take that into functions instead. So we're looking between a and b again. We're saying that f of x is the top function, g of x is the bottom. So what we're doing here is we're saying that if we're finding our area, the outer radius is the upper function, which means that we're going to have f of x. So we're going to have pi times f of x squared. And the inner function is the lower function, so g of x squared. And so this is going to color then how our method looks. We'll call this the washer method because a washer will have a hole in it. And this gives us our area. We integrate that. So you take the upper function, square it, minus the lower function, squared, multiply that whole thing by pi, integrate that. So that's going to be our washer method, how we find the volume of a solid that's got this kind of hole running through it. We could, again, do the same thing with y if we replace all the x's with y's. So let's go ahead and take a look at something like this. The region R is bounded by the graphs of square root of x and x squared. So square root is going to be this guy here, and x squared is going to be this guy. So this is going to be my f of x, and it's going to be g of x. And it says between x equals 0 and 1. Keep in mind, it's not always going to be obvious where these points should be. Sometimes you'll have to find the intersection. Remember, set these guys equal to each other and solve. All right, so here's our region then in between those guys. And we're revolving that about the x-axis. So again, we're going to have a solid that's got a hole in it. Remember, the outer radius is the upper function. So if we're looking at our volume here, pi times big radius squared minus small radius squared. Upper function is the big radius. So root x squared minus the smaller radius, which is my lower function, square that. And we're looking from 0 to 1. All right, so we'll go ahead and start cleaning this up and then integrating. So we'll bring the pi out again. We've got x minus x to the 4th dx. Right, the square and the square root cancel, and then square the square. All right, so we've got pi times, we'll go ahead and run the power rule here. We've got 1/2 x squared minus 1/5 x to the 5th. And this will be evaluated from 0 to 1. So we'll evaluate, we plug the 1 in, we've got 1/2 minus 1/5, minus, plug the 0 in, we got 0 and 0. So pi times 1/2 minus 1/5. That's pi times 5/10 minus 2/10. So that's pi times 3/10, which is 3 pi tenths cubic units. All right. And so the last one we'll look at here is going to be, again, about the y-axis. So we'll go ahead and take a look at this one. So let R be the region bounded by y equals x, y equals 2x. So we do have to determine which one is which. We see that, let's see, this line is a steeper slope. It goes through the point 1, 2. So this is going to be y equals 2x. So that means that this one is y equals x. And lastly, y equals 6. So we're taking this horizontal line here, y equals 6. So this is our region in between all those guys. Find the volume of the solid generated when R is revolved about the y-axis. So we're talking about taking the solid, revolving it this way. So again, we're going to have a hole in it. And so we're going to have to go ahead and figure out which is the right function versus which is the left function. We're also going to have to solve for x. Right, so if y equals 2x, x equals 1/2 y. So that's another way of writing this function is x equals 1/2 y. And y equals x is the same thing as x equals y. And we can see here that x equals y is the right-hand function, which means that is our outer radius. So if we're looking at our volume here, outer radius is going to be y equals x, or sorry, x equals y. So y squared minus the inner radius squared. That's our 1/2 y. And this is taken in terms of y, so dy. And lastly, we do have to figure out our limits of integration. So down here, they intersect at y equals 0. Also x equals 0, but that's not really what we're interested in. And we're going all the way up to y equals 6. It was actually given in the problem. And you can see that that's kind of where our last circle then would be. Or our last washer, rather. Sorry. And so again, we'll integrate this. Bring the pi out. Pi squared minus 1/4 y squared dy. And so if we combine these, we've got 1 y squared minus 1/4 y squared. That's 3/4 y squared. And just because I know I'm going to be using the power rule and getting a 1/3, I'm only going to take out the 1/4. So I'm going to have pi over 4, 0 to 6 of 3y squared dy. So we'll run the power rule through this. We'll run this through the power rule, rather. Y cubed, divide by 3, the 3 cancels. And so we get pi over 4 times, let's see, 6 cubed minus 0 cubed. So brackets are unneeded. I could just use parentheses. Six squared is 36, so 6 cubed would be, let's see, multiply 216. So pi over 4 times 216, and there is something that I can cancel here, right? If the last 2 digits of something are divisible by 4, the whole number is divisible by 4. So we'll go ahead and see here, 4 goes into 25 times with 16 left over, so 54 pi cubic units. All right, let's move on to the next one then. Find the volume of the solid obtained if the region bounded by the graphs of y equals x, y equals 0, make sure that we're keeping track of this here, and x equals 3. So looking at this region in here, is revolved about the line y equals -1. So this is the first time we're dealing with something that is not being revolved about our axis. So normally if we took this guy revolved about the axis, this would just be a disk method, and we wouldn't have to do any subtractions or anything like that. But now, we're revolving it about this line, which means we're actually going to be reflecting. about that line. So if our reflection is about that line as well, we're looking at sort of our mirrored region being down here. And so if we kind of take a disk here, we will end up making it into a washer because we'll have this hole in it here. And I am struggling on making those circles, so I'll go ahead and actually draw in my points. So you can see that our inner radius is actually going to be consistent. We're only just going to have this little bit cut out. It's always the same inner radius. So it's really just going to be a cylinder that we're cutting out. And so when we go to integrate, first off, since we are doing this about a horizontal line, we are going to keep things in terms of x, right? The outer radius is still going to be our function height, but we have this extra little space, right? If we just take our function value, it's only going to give us the space between the axis and the function itself. But we have this extra bit here between the axis and -1. So what we'll do is we'll make our outer radius x plus 1. So x plus 1 squared. That's our outer radius. We have to add in that extra little 1 there. The inner radius is just going to be 1. It's just the distance from the line up to our function. So again, we'll bring the pi out, and that's really all there was to this. Oh, I guess we have to figure out our x's, right? 0 to 3. X squared plus 1 times x times 2 is 2x plus 1 squared minus 1 squared. So we've got pi times the interval from 0 to 3 of x squared plus 2x dx. And again, we just run this through the power rule. And we'll go ahead and evaluate this from 0 to 3. And so when we do that, we've got 1/3 times 3 cubed plus 3 squared minus 1/3 times 0 cubed plus 0 squared. Those guys are all gone. 1/3 times 3 cubed just turns this guy into 3 squared. So we got 3 squared times 3 squared. Or sorry, plus 3 squared. So we got 9 plus 9. And so we get 18 pi cubic units. All right, and that's going to be then the end of this section on general slicing, disk method, and washer method. So next section we'll add in one more different type of slicing that will open up our ability to do all kinds of different functions. There are limitations on the disk and washer method. There are certain types of functions that get really tricky. Similar to the way that if we had sort of a function on top of itself in just doing regions between graphs would run into trouble. Same kind of idea. There are some functions in here that if we kind of have the function that's maybe got 2 radii involving itself, it's going to be really tough to do. So we'll go ahead and fix that next section.